The population of Adamsville grew from 8,000 to 14,000 in 6 years. Assuming uninhibited exponential growth, what is the expected population in an additional 2 years? So first I want to start by focusing on our assumption that we have uninhibited exponential growth. So that's what's referring to the model that we'll use to answer this question. Uninhibited exponential growth follows this model of A equals A naught e to the kt. Sometimes when we're talking about population, however, they might use P instead of A. So it might look like this. P equals P naught e to the kt. So this is the model that we're going to substitute some of this information in. And in the first sentence, it states that the population grew from 8,000 to 14,000 in 6 years. With just this bit of information, we're going to be able to find K, which stands for the growth rate in this problem. Maybe it's a good idea to start with that. This formula, P equals P naught e to the kt. Let's go over what each one of these stands for. P naught would be our initial population. So P naught is initial population. K is our growth rate. T is time. And then P would be our ending population, or population after time. So using this information in the first sentence, that we grew from 8,000 to 14,000, gives me values for P naught, so our initial population, I apologize, I'm having some trouble with my pen here. So that 8,000 is P naught, our initial or starting population. Then that 14,000 is our population after a time period of 6 years. And so our only unknown value is K, the growth rate. So with that information, we're going to be able to find the growth rate, which is what we need for our model. So we're going to substitute these values into our exponential growth model. P equals P naught e to the kt. In for P, we have 14,000. P naught is 8,000. T is 6, and remember K is our unknown. So once we've substituted in these values, we want to solve for our missing value, which is K. And since our missing value, our variable, is in the exponent, we have an exponential equation, and we'll use our exponential techniques to solve. We first want to isolate the exponential by dividing both sides by 8,000. So this reduces down, those zeros cancel out. We have 14 over 8, and 14 over 8 reduces down to 7 over 4. The 8,000s cancel on the right-hand side, and we're left with e to the 6k. So now we have our exponential isolated, and we want to solve for that k. When we're solving exponential equations, we have 3 main methods for solving those exponential equations. We can make the bases the same. which in this example we can't do. We can convert to a log, or we can take the log of both sides. I prefer to take the log of both sides. So I'm doing natural log on the left and natural log on the right. Once you introduce the logs, you can use log properties, and there's a log property called the power rule, which allows you to move this exponent to the front. It becomes the coefficient, so we have 6k natural log of e. On the other side, I'm just copying down natural log of 7 over 4. Natural log of e is equal to 1. So 1 times 6k is 6k. And then we can divide both sides by 6 to get our value of k. So we have that k equals natural log of 7/4 over 6. I'm going to type this into my calculator to get a decimal approximation. However, I'm probably not going to use that decimal approximation because with these problems, sometimes rounding too early can cause your answer to be wrong later. You want to save your rounding to the end of the problem if you can. So natural log of 7/4 over 6 gives me 0.093. Let's round to 3 decimal places. 0.093. So approximately 0.093. So this is our growth rate. And that growth rate came out to be positive because the population is growing. If the population was getting smaller, that rate, this k, would come out to be negative, and we would call it a decay rate instead. So now that we have the growth rate, we can now answer the second part of the problem. It says, assuming uninhibited exponential growth, what is the expected population in an additional 2 years? So we want to go 2 more years and find out what that population would be. So there are 2 ways that you can go about this. You can, let me write those 2 ways. So you can use an initial population of 8,000, like we did before, and then our time would be 8 years in that case. That's the 6 years plus the 2 additional years. Or you could calculate this problem with your initial amount being 14,000, and then you would, because you've already done the 6 years, you would only use the additional 2 years. Both should get you the same answer, and we'll substitute into our model. So remember that our model is this right here, P equals P naught e to the kt. So that's P equals 8,000 e, and we're going to use that value of k that we found, a natural log of 7/4 over 6 times a time of 8 years. And the other way, we would use an initial population of 14,000 e to the k, that's natural log of 7/4 over 6 times 2. Now, before I enter this in my calculator, I do like to write this a little bit different to make it easier to type in the calculator. I like to put this time in the front. So I'm going to write this as 8 times natural log of 7/4 over 6. And the same thing with this one over here, 14,000 e to the 2 times natural log 7/4 over 6. So we're going to type these in our calculator to get the population with an additional 2 years. We've got 8,000 e to the 8 times natural log. And so the reason why I moved that time to the front is because you have less parentheses that you need when you type this out if you put that 8 in the front. So 8 natural log of 7/4 divided by 6. And we have 16,870. We'll round to the nearest person, so that's 16,871. And let's type the other one to make sure it comes out to be the same amount. We have 14,000 e to the 2 times natural log of 7/4 divided by 6. And you can see we got the same value under both scenarios. All right, so we've answered the question. The expected population in additional 2 years is 16,871. During a research experiment, it was found that the number of bacteria in a culture grew at a rate proportional to its size. At 5 a.m., there were 2,000 bacteria present in the culture. At noon, the number of bacteria grew to 3,100. How many bacteria will there be at midnight? So, we're assuming that we're following another exponential growth model. We're going to use A equals A naught e to the kt. So let's remember what each one of those stands for. You have A naught, which is the initial amount. You have K. This is either your growth or decay rate. And in this example, our bacteria culture starts at 2,000 and grew to 3,100. So this one is going to be a growth rate. And whenever it's a growth rate, K will come out to be positive. And then T stands for time. And A, this is going to be your amount after time. So we need to find the growth rate. And with the information that was given here, at 5 a.m., there were 2,000 bacteria. And then at noon, we have 3,100. So we have at 5 a.m., which we'll consider our initial time, we have 2,000 bacteria. And then at noon, okay, so we're going to count from 5 a.m., that would be 6, 7, 8, 9, 10, 11, 12. So that's 7 hours later. We have 3,100 bacteria. So with this information, we're going to be able to calculate the value of K, our growth rate. And once we get the growth rate, we'll have a complete model for this scenario, and we'll be able to answer this question that is posed at the end. So we're going to start by finding that growth rate. So using our exponential model, A equals A naught e to the kt, we have our ending amount being 3,100, amount after time. Our initial amount is 2,000. And our K is our unknown, and we have a time of 7 hours, which has passed. Now this is our variable K, which we're trying to solve for, and it's in the exponent. So we're going to use our exponential methods to solve. We're going to isolate this exponential by dividing both sides by 2,000. We can cancel those zeros out, and that reduces down to 31 over 20 equals e to the 7k. We can solve this by either making the bases the same, taking the log of both sides, or converting to a log. Making the bases the same is not possible here, so we'll use one of our other methods, and I prefer to take the log of both sides. I'm doing natural log on the left, natural log on the right. Once you introduce the logs, you get all of the properties of logs that you're available to use. And one of them is the power rule, which allows you to move that power out of the exponent and into the coefficient. We have 7k natural log of e. On the left, we'll have natural log 31 over 20. Natural log of e is 1, so this simplifies to be 7k, because 7k times 1 is 7k. And then we can divide both sides by 7 to get our value of k. We write it out over here. We have k equals natural log of 31 over 20 all over 7. I'll type that into my calculator to get an approximation of the growth rate. Remember we said it should be a positive value. So you can follow along with the buttons that I push. Down here at the bottom it says key press history. We've got natural log of 31 over 20 over 7. And so our growth rate is 0.063 if we round to 3 decimal places. And as I've said before, we are not going to use that decimal approximation. We're going to use the exact value because rounding early on in this problem can cause rounding error once you get to your answer. So now we have our model for this situation, and our model for this situation is A equals A naught, our initial amount of 2,000, e to the k, we just found k, natural log of 31 over 20, divided by 6, t. So now that we have this model, we can substitute any value of time into this model to find out how many bacteria will be at that time period. So we're interested in how many bacteria will there be at midnight. So at midnight, that would be a 12 additional hours from noon. So that would be 19. 12 plus 7 would be 19. So we'll substitute in for a time of 19 hours. And as I've said previously, I like to write that 19 in the front because there are less parentheses that need to be typed into the calculator that way. We'll type our expression into the calculator, 2000 e to the 19 times natural log of 31 over 20 over 6. So after 19 hours, we will have 8,012 bacteria. We'll round to the nearest whole number. So at midnight, there will be 8,012 bacteria present. Thank you for checking out my videos. Have a great day.